Biostat 66111, skills for the rest of your life, bootstraps and probability, it's the bread and butter, baby, what's your jam?
Greetings, Bio 6611. In this lecture, we're going to introduce the foundations of simple linear regression, which we will spend most of the rest of the semester building and exploring off of. We'll first touch on the idea of correlation before motivating simple linear regression, introducing the regression line, and also introducing the assumptions we make when we conduct a simple linear regression. For the purpose of motivating simple linear regression, we're going to first talk about Pearson's correlation. When given two continuous variables, one way to measure their association is through correlation. This is especially useful if there's not yet an identified response variable. For example, if we have two continuous measures and we don't necessarily think of one as the outcome and one as a predictor. Pearson's correlation coefficient, then, is used to measure the strength and direction of the linear association between the two variables. It can be used to, therefore, estimate the population correlation, which we designate rho, and it's defined by the following formula. We generally represent it with a lowercase r, and it's equal to the product of the difference of one of the continuous variables minus its mean times the other continuous variable observation minus its mean, then divided by the square root of the squares of both. The correlation itself is a dimensionless quantity. In other words, it's independent of the units of measurement we used for x and y. Another thing to note as well is while we're focusing on continuous measures of correlation with a linear assumption, there are measures of correlation that can handle ordinal, binary, and nonlinear associations. So what are some properties of this correlation coefficient? Correlation can range between -1 and 1. We have the following general properties and conditions. If r is greater than 0, then as x is increasing, y is also increasing. And we would say the two variables are positively correlated. And if we happen to see that r equals 1, it would be a perfect positive correlation. This is in contrast to r being less than 0. In that case, as x increases, our other variable y would be decreasing, and the two variables are said to be negatively correlated. Again, an r equals -1 would represent then a perfect negative correlation. Finally, with point 3, if r equals 0, then we would conclude that there is no linear relationship between x and y. Or in other words, the two variables are uncorrelated. We can also note if we happen to have the covariance between x and y, and we knew that it was equal to 0, we would then right away know that the correlation between those two variables will also be equal to 0. So to summarize these ideas, the correlation coefficient is a measure of the strength of that linear trend relative to the variability of the data around the trend. Thus, it's dependent on both the magnitude of the trend as well as the magnitude of the variability in the data. Here are some examples of correlation just to get an idea of the general sort of trend we might expect to see from Wikipedia. And there's a few things we can note based on sort of walking through these different rows. In the top row, we see some trends of correlation based on just an increasing amount of variability. We see if we start at the far left, we see this perfect positive linear correlation because as x increases, y also increases, and it's in a perfect linear line. Though as we go to the right, we see that the variability is increasing, so our correlation, while we can still see a general positive trend in both of these, is getting more uncertain until we essentially get to our middle point here, 0, where there's really no direction that we can immediately take away from that figure. So we would think that they're uncorrelated. We can then see the same pattern happening in reverse as we get increasingly negative with our correlation, with decreasing variability till we get to the far end -1. In the second row, we can note similar trends. However, in this case, we're illustrating that the actual magnitude of that slope is not what's important when it comes to correlation. Instead, again, we're looking at that linear relationship between x and y. So each of these first three in the second row have a correlation of 1, because even though the magnitude of the increase is getting less steep for that slope, there is still that perfect linear relationship. Likewise, at the right-hand side, those three all have a perfect negative linear correlation. We can note as well there is this middle point, which is a perfectly horizontal line, which is an undefined measure of the correlation in that case. Finally, we can note that on the bottom row, we have a bunch of correlation examples that are 0, which are just presented to illustrate that, we have these different shapes our data could take, where we have sort of this sinusoidal curve, various forms of squares on different angles, a nice little happy face, 2 bananas, a donut hole, or actually a donut, then a bunch of donut holes. But essentially, with these data, the correlation would be 0 because any line we would draw through, we would have no way of identifying a meaningful direction for that linear trend of the data. They may be correlated in other ways, but not with our Pearson's correlation. So let's look at just a very quick, simple example of correlating 2 lung function meters. We have peak expiratory flow rate, or PERF, which can be measured using either the right peak flow meter or a mini right peak flow meter. So we might ask ourselves the question, in a hypothetical situation, do their measurements correlate if I had individuals take a measurement on both? We see a scatter plot with a linear trend line plotted over it on our figure here. We see that for the most part, it does in fact look like the data follows a linear trend. And if we calculate the correlation for our data, we would get a value of 0.953, or a very strong positive linear correlation. One thing to note, however, is that this is a very different question than asking if the measurements are in agreement. In that case, if we want to look at the agreement or consistency of measures, we have other metrics we can use than correlation. So with that idea of correlation, we'll now transition to simple linear regression, and we'll also see some associations in the following weeks between the idea of correlation and some summaries of simple linear regression. But before we get too deep, we're going to introduce a motivating example which we'll see throughout the rest of the semester, looking at lung function in children from a data set in the Rosner textbook, originally published in the American Journal of Epidemiology in 1980. The study objective was to describe how lung function develops in children and how smoking may affect that development. The design of their study was a cross-sectional survey of a random sample of children between ages 3 and 19 from the East Boston area, of which ultimately we have 654 with usable data, which you can find on our course website. The variables measured included FEV, or forced expiratory volume, age, sex, height, the current smoking status. FEV specifically measures how much air a person can exhale during a forced breath, with a higher FEV indicating a better lung function. Now, in the context of what we'll be exploring, we're going to see these definitions of these variables below. The outcome variable we will consider is primarily going to be that FEV measurement. Depending on our context, as we build from simple to multiple linear regression, we'll have the potential for multiple primary explanatory variables, which could be in our case age, sex, height, or smoking status, depending on the question of interest. And if we do include multiple variables, whichever one is not our primary explanatory variable will just be considered a covariate. Again, it will depend on the context of the problem at hand. So let's start building towards a motivating reason for linear regression and why we would need to expand upon our previous repertoire of either methods from prior stats courses or the ones we've covered so far in 6611. So let's first assume we have a continuous outcome FEV, but we have no covariates. So if the only information we had about a child was their study ID number and their FEV measurement, we might say that our best guess for FEV of any given individual would just be the sample mean. In other words, the expected value of y, our outcome, or we can just plug in FEV there, will be equal to the formula we have for the sample mean, y bar, which if we actually loaded the data in R, we would calculate and find out that the FEV on average is 2.64 liters. At the right-hand side, we see a scatter plot where the x-axis has the different identification numbers in the data set and then just plots the FEV observations. And unless the data was organized in a specific way, we would expect kind of what we see here, which is a random smattering of FEV observations. Now, what if we move, though, into the context where we have a continuous outcome, but a binary covariate? In other words, maybe it's something like we knew the child is a non-smoker or smoker. What would be our best guess then for the FEV of an individual if we have that additional information? And in this case, let's call this expected value y given x, or e of y given x. Now we see at right-hand side here, we have a scatter plot type figure where we plot out just a non-smoker or smoker status based on that cross-sectional survey. And we plotted then the mean within each of those groups, which we see summarized over here to be 2.57 liters and 3.28 liters for non-smokers and smokers respectively. So we may ask ourselves the question then, with this information, how could we test whether FEV differed for smokers and non-smokers? Now I'll give you a second just to think about some possible solutions, and then we'll discuss them together. Okay, so some things we could use that we've covered in the semester so far, or have expected as a prerequisite for the class, could be a two-sample t-test if we were willing to assume that they're approximately normal or normality is met, or the central limit theorem's kicked in. Based on some recent material as well, though, we could do the Wilcoxon rank sum test, the WRS, or we could even do maybe some sort of permutation test if we didn't want to assume anything about the distribution. So we have a couple options there for what we could do to actually test this relationship. However, what could we do if we have a continuous outcome but also a continuous covariate as a predictor? For example, if we knew the child's age, what would be our best guess for the FEV of each individual? And again, we can sort of describe a similar pattern that we saw before, just with more categories than smoker and non-smoker. For example, we see our scatter plot over here is now plotted people based on their age and their recorded FEV, and we do see some sort of general trend taking place in a couple other takeaways. But first we can focus on the question of, let's say, what if we knew the child was 15 years old? Well, in that case, we could look at the sample of 15-year-olds on our figure here, and we could then take the average within those individuals, or that subsample of our overall sample, and see that the average FEV is 3.5 liters. If a child was only 3 years old, over here on the far end of our distribution or scatter plot here, we could take those two observations and calculate the average FEV as 1.2 liters. Again, though, we can note that it's based on only two observations, which may make us a little wary about drawing any grandiose conclusions. Now, the one challenge here right now is that if we calculate the mean within each of these groups, we see we don't have a very smooth line, and there's some noise going on in the data, especially as we get to the younger or older ages. And also, we don't have any way of formally testing this potential significance of age as a predictor of FEV. And this is where we cue simple linear regression, SLR, to come to the rescue. Our goal with simple linear regression, or regression more generally, is that we wish to model the distribution of some continuous response variable, for example, our outcome FEV of interest here, across groups defined by a single predictor. In this case, age, which we saw on the previous slide, could treat as a bunch of categorical variables, or perhaps we'd like to treat as that one predictor continuously. To do so, we'll identify a regression line, or in other words, something along the lines of FEV equals what we're calling beta naught plus beta 1 times age. And this will be a linear approximation to the graph of averages we saw on the previous slide. This regression model then can be used to answer some commonly encountered statistical questions relating to prediction, quantifying a distribution, or comparing distributions across groups. And each one will have its own sort of considerations as we're accounting that from a predictive or a descriptive approach. Just some more motivation, and we'll see this throughout the following slide sets, which will expand upon these ideas and derive some of these features, but the regression model will allow us to make inferences about groups that have few, if any, subjects by borrowing information from other groups. So we can imagine that potentially in our FEV example from before, we didn't have as many very young children or older adolescents. So we can potentially leverage the average trajectory we see, if we think the assumptions we'll discuss later are met, to try to fill in those missing pieces of information. this is really thought of as interpolation to unobserved groups, and it's considered less risky than the opposite of extrapolation outside the range of predictors included in the regression model. Or in other words, we can imagine here, we can interpolate between any two ages. For example, the data is in terms of whole age numbers, but we could then with a regression equation predict the expected FEV at someone who's 13.2 years old, or 4.5. This is different than that idea of extrapolation where maybe we say, well, what's a 1-year-old's expected lung function, or someone who's older than 19? Now we can note that there's different mathematical models that could be appropriate to model the distribution of any given y across some value or values of different x's. We're going to consider right now a straight line for simple linear regression, but we'll also see later in the semester we can do parabolas, log functions, and other ways of trying to address the appropriateness of the model. But ultimately, putting that aside, we're really interested in finding the best model we can that describes our data while also trying to be parsimonious. So we're constantly in this idea of trying to balance a simpler model with as few predictors as possible with something that's appropriately and adequately explaining the data. And sometimes we'll choose these models based on an experience we've had previously or maybe some knowledge of theory. But for our sake, we'll begin by assuming a straight line model with just a single predictor, which will have this structure here of, again, y equals beta naught plus beta 1 x1 plus this epsilon term. So what is that equation actually representing? Here we'll see the regression line. So that general format is the regression model, and its components include beta naught, the intercept of the line, beta 1, the slope of the line we're going to fit, and then epsilon, the error term. Well, we'll walk through some of the considerations and properties on the following slides. But we can also note briefly, this is the theoretical model we're using, but in practice what we're actually going to draw inference off of and interpret is the predicted value of y based on some given value of x. For example, we'll put hats on these parameters to show the predicted value of y hat, is going to be equal to some fitted regression line where those beta naught hat and beta 1 hat are represented by things that we can derive later on. So let's start with beta naught, the intercept. The intercept is the expected value of y when x is equal to 0. Or in other words, we can write it mathematically here as e of y given x equals 0. Now, oftentimes we do not actually observe values of 0 for x, for example, an age of 0 or a brand spanking new infant. And this could be problematic for a few reasons, or at least things to keep in mind when potentially interpreting this term. First off, if we don't have those observations in our data set, we would be extrapolating to the estimated mean when x equals 0, and again, we should generally avoid the issue of extrapolation. Another challenge as well is that besides the fact we're extrapolating, in many cases, even if we did extrapolate, it doesn't necessarily make biological, clinical, or contextual sense to interpret this term. Again, it doesn't necessarily make sense that we would have an infant able to take their FEV measurement right at birth, especially with the setup of the cross-sectional survey design that we're using. What we're usually more interested in interpreting in many cases is beta 1, or our slope term. Now, the interpretation we'll use throughout the rest of the semester for these terms is at the top here, where beta 1 is the expected change in y, our outcome, associated with a 1 unit increase in x, our predictor. And it's meant to be very general here for 1 unit, but it will be in terms of whatever we're modeling. So we see a couple graphs here below and a couple general conclusions for how to interpret this parameter. For example, if beta 1 is greater than 0, then as x increases, the expected value of y is increasing. And we see that over here for our plot of FEV by age. Generally, as each person increases in age, their FEV goes up. If beta 1 is negative, as we see here with the number of cigarettes smoked as our predictor, then as x increases, the expected value of y will decrease. And unsurprisingly, the more cigarettes one smokes, the lower their FEV will be. And then if beta 1 is equal to exactly 0, we would say there is no linear relationship between x and y. For example, if we're getting back to the idea of calculating our average FEV across IDs, there's no reason for us to expect there to be a meaningful ordering necessarily. We can note that these interpretations of beta 1 greater than 0, less than 0, or equal to 0 are for continuous predictors that we've plotted to the right. But they'll also generally hold for categorical predictors that we'll talk about later, but they'll be interpreted in that case with respect to some reference category. We can also note as well there's some strong connections between the general interpretation of the Pearson correlation coefficient and our slope parameters. And finally, we have this persnickety error term epsilon. We generally don't expect the linear relationship to hold exactly for all individuals. So the error term is included to represent this variability in our sample. And it's going to represent the variance of y given some value of x. Now here's where we get a few assumptions that will preview our closing slide in a few minutes, but the error is assumed to follow a normal distribution with mean 0 and a variance of what we'll call maybe sigma squared e, where epsilon will be then distributed, as we see here in our statistical notation, as a normal distribution mean 0, variance sigma squared e. If the model does happen to fit all individuals perfectly, then we would be able to note that our estimated variance of the error term here is equal to the variance of y given x. Otherwise, we'll have this relationship where it will be biased upwards. It will again account for that variability in our sample. Now, in reality, we don't know the actual error, but we can estimate this population parameter by calculating what we will call a residual. This is known as the difference between a fitted and observed value, or specifically speaking here, E sub I is equal to our observed data y sub I minus whatever our predicted value y hat sub I is for a given individual. We'll expand upon these ideas, terms, and different properties in the subsequent lectures, but before we close with our SLR introduction, let's introduce some assumptions. Generally speaking, there are 5 assumptions we'll make when we're fitting a simple linear regression. The first is existence. For any fixed value of the variable x, for example, an age at 15, y is going to be assumed to be a random variable with a certain probability distribution having a finite mean and variance. In the case of a linear regression, we also unsurprisingly assume linearity. The mean value of y, or some transformation of the value y, mu y given x, is a straight line function of x, or some transformation of x. We'll see later on in the semester that we can transform either our outcome or predictors, or both, to achieve some of these assumptions that could potentially be violated. We also make the assumption of independence, where the errors epsilon sub I are independent. In other words, the y values are statistically independent of one another. And we can note if this is violated, there are fancier methods that we can use to account for this correlation. Fourth, we'll assume homoscedasticity. The errors epsilon I at each value of the predictor x sub I will have equal variance. In other words, the variance for y will be the same regardless of whatever value of x we choose. So we can see this written out here as the sigma squared y given x will be equal to any given value of x we might give. And finally, one of the important assumptions as well is that we are making an assumption of normality. However, it's not necessarily at the level you might think. What we're really assuming is that the errors epsilon I at each value of the predictor x sub I are going to be normally distributed. In other words, for any fixed value of x, y will have a normal distribution. But this does not mean that y itself has to be normally distributed. Just that when we fit the model and look at these residuals, we're making an assumption then that the underlying errors themselves will be normally distributed. In closing, to help visualize some of these assumptions, we can see this nice figure here, and where we have this linear regression line right here, and we see a couple different data points for different values of x. And what we see basically is that each of the points that we have on the line is that mean value, and then around that mean value for each level of x, there is an approximately normally distributed shape of observations centered around that mean. So this helps to illustrate that idea of linearity, the equal variances of that homoscedasticity assumption, and also the general idea of normality. At this point, we'll stop here before walking through in the following lectures more properties, derivations, and actual interpretations of how we can fit these regression models.